Our speaker is David Hewson from Cray Limited in Bristol. David is a senior engineering manager at Cray Limited with over 25 years experience in high-performance networking. David is currently a member of Cray's European R&D Centre. Previously, he was founder at Nodal, a Bristol-based Ethernet switch manufacturer and responsible for the software development and ASIC verification. His talk is on verifying verification using open source to roll urine.
I'm going to talk about some stuff that we did at Nodal probably a couple of years or so ago. This was actually work with a colleague of mine, Peter Hediger, who's now at Exmouth, and it's really about how we could use kind of open source tools and commodity compute to create our own kind of mutation testing environment. So unfortunately, I put this slide up kind of without realising I was going to be last. So you're all converts to mutation testing now. So it kind of says what it says really, that the traditional model of doing things, of test plans, functional coverage, assertion coverage, is all good if you trust your verification engineers to be superstars. And we kind of realised that if you could do that, then you could probably trust your RTL designers to be superstars as well. So really we need to quantify kind of how good the test benches are. Yeah, so the thing that occurred to us is kind of computers getting an awful lot cheaper these days. So if you start looking at kind of commodity hardware, you can get real fast multi-core processors. You can get desktop motherboards that are real cheap. Memory is cheap, and we don't actually need any storage on our compute nodes. So we use the kind of Google-inspired kind of rack technology to basically build compute racks with minimal packaging, and that meant that we could get the cost of a core down to, this says $50. I think if you work it out these days, it's more like kind of $25 or so. And when you've got your core costs down that low, then you can't really be affording to pay much on your software either. So we were looking at using open source software to create an environment to do mutation testing. So our verification environment that we used was based on System C, which meant that we could look at tools like Verilator, which is I call it a simulator. It's really more of a compiler that compiles Verilog into C++ System C. So we could use that, which is an open source project, to run our verification environment. And there's also a number of good batch systems out there that are open source. So in our case, we used some Grid Engine. And then the final thing that kind of allowed us to do this was Verilog Perl. So what's Verilog Perl? So it's part of the Veripool software environment. It's all publicly licensed open source, written by Wilson Snyder, who also is responsible for Verilator. And it's basically a building block for Verilog support in Perl. So there's three kind of main modules to it. The first one is just kind of general kind of background stuff for Verilog language keywords. It has a preprocessor, so that basically allows you to take your Verilog source code, go pass it to the preprocessor, get rid of all your tick and clues, tick defines and stuff. And then it has a parser which can basically invoke callbacks in Perl for language tokens as it goes through it. And it supports most of the system Verilog keywords. So what did we do? So we basically extended the parser to recognize expressions in our Verilog. And in our kind of style of Verilog, kind of expressions relating to wires and signs were suitable. We would then build a abstract syntax tree out of it. So as you see, for each of the nodes in the tree, we'd look at various different operators. So unary operators, binary operators, concatenations and symbols, and then we would generate mutations for each of these nodes in the tree. So again, with a unary and binary operator, you can replace the operands of the same geometry, so replace a plus with minus, that kind of stuff. Binary operands, you can move the left-hand side, right-hand side, reorder them. Concatenations, reorder the elements, and obviously symbols, you could just invert. And so from this, we would then build a list of code changes that we could then apply to our source code. So here's an example. So as you see, we've kind of got one expression in the code, and what the tool would do was generate this list of possible mutations on it. And so the interesting thing is kind of the two middle columns are essentially saying which line of code to replace out of the source code, and the right-hand side is saying what to replace it with. So, and as you can see, we've replaced various operands with their inversion, replaced kind of pluses and minuses, that kind of stuff. So then, essentially, for running it, we'd create some scripts that would run it using part of our regression system, we'd just modify it slightly. So create the mutated source code from one of those lines of differences, we'd compile the design, obviously with verilator, that's full compile. With commercial simulators, you can do it a bit more efficiently. And then we'd execute the test suite until the first failure. One of the things that we did was we also used some random seeds as well, because getting the correlation between your seeds between a commercial simulator and an open source simulator is kind of hard. So although kind of seeds that cause good coverage in a commercial simulator, they'll probably cause good coverage in an open source simulator as well, but they might not run it identically. So we also ran some random seeds as well. And then we could also prioritize which tests we ran by where the mutation is applied. And then I think the one thing that's kind of important is as we were running different tests that hadn't been run before, because we might have used a new random seed, it's always a good idea to run it again with the change removed, because you never know, we might have stumbled across a real bug. Batch processing, so again, kind of as people know, kind of each mutation test is completely independent, or should be. Each mutation that you apply can actually lead to a large number of tests that you want to run, and we therefore have a vast number of concurrent jobs that we could run. And as Verilator, we've got no licensing limitations, and we can run all of those concurrently. And with a commodity kind of rack like we were building, we could get maybe 500 cores in a 19-inch rack. So we also had to adapt some of our build and run scripts to make this work. We were using Cadence eManager for coverage runs, and we only have one license because Fred was a bit mean. So we actually had to develop some scripts for running it ourselves, just to submit the jobs and cancel them. And again, the mid-engine would mean that we can manage our resource. So we could run all these jobs at lower priority just to soak up any background idle time. And of course, as people said before, kind of once you see a failure, that's good enough, you can stop there, really, so for a particular mutation. So some of the challenges that we faced, one of the things that we did kind of notice is if you apply some mutations, then what happens is the job just kind of times out, and because it hangs up. And kind of if you're doing testing, a job that times out is fine because that's failure. But if you're actually looking for a mutation, that's not a failure. You actually need something that's positive, that says it's a positive failure that you've detected. So we recognise that. Correlating what the mutation did and why you didn't check it is also kind of hard, as people said earlier. So it's a time-consuming process, really. But to some extent, it's not really different to understanding kind of how you go about finding missed expression coverage, really. Again, as we've heard, kind of some code changes that some mutation you might apply would actually not have any discernible effect. And when you go and analyse it, you discover there is actually nothing. It has no effect, really. So because it's dead code or whatever. And again, I guess you could use formal equivalence checks or something like that. I mean, obviously, there's tools like Certitude actually recognise that because they recognise that it actually truly doesn't mean anything. And again, something that someone came up with is kind of how do you try and do this kind of early in the test cycle rather than leaving it for the last bit when you think you're all finished, then you run your mutation testing and you discover that actually you're nowhere near, really. So we looked at kind of ideas about how we could use kind of expression coverage to try and remove or ignore mutations that we kind of knew were not going to have any effect. And then kind of conclusions. So as a result of this, we did actually find some real bugs, really. So it was worth the time it took. I mean, actually to put all of this together probably was only a couple of months of effort, really, because and it was well worth it. I think also mutation testing is just kind of one way of improving quality. I mean, writing verification code is actually really a software development process, really. And so some of the ideas that people were talking about earlier with kind of essentially unit testing continuous integration as part of the verification development environment is very good. I kind of like the idea that you could kind of, as you're developing your test bench, you could quickly see, you could have a quick run of Certitude or something that would tell you that it hasn't got any worse. So the parser and mutation generation code that we developed, because we weren't going to be taking it anywhere, we donated it to Mike for what he wants to do. I think the final thing kind of is you can never have too much compute power, to be honest. So, okay, thank you.
Hi, I noticed in the previous foil that you mentioned that you had to script the submission of jobs, and I was wondering that let's see, Grid Engine has job arrays, and I wondered if you use job arrays because it should be just one job array.
No, we didn't actually, because I didn't know about job arrays. But yeah, I mean, kind of one of the reasons we used Good Engine was because we were using eManager, which has just got a push button that you check on it.
eManager doesn't support job arrays very well.
No.
Job arrays are very good for submitting thousands of jobs that are very simple, except with small changes, which is what you do.
Right. Yes. Yeah. Okay.
Any more questions from Bristol? Yeah. Share and enjoy, as they say. Yes. Any more questions? No? Okay. So thank you, David. Thank you very much.